Welcome to our presentation titled Bridging Simulation and Reality, a Digital Twin Approach for UAVs. This work explores how digital twins bridge the gap between simulation and reality in unmanned aerial vehicles, or UAVs, ensuring a robust and precise integration that facilitates safe operations. This diagram illustrates the control architecture used for developing and validating UAV controllers, organized into three main subsystems: the high-level control subsystem, the digital twin subsystem, and the real drone subsystem. The high-level control subsystem includes the advanced robot controller, which processes information about the UAV's position and orientation received via robotic operating system and generates commands sent to either the drone or the simulator. In the digital twin subsystem, we use a nominal UAV model and an advanced simulator, such as DJI Assistance 2, to replicate real flight conditions. These tools allow us to evaluate performance before implementing the controllers on the physical drone. Finally, in the real drone subsystem, the physical UAV executes the controllers and collects experimental data. Here, the control authority manages whether the commands come from manual control or the DJI SDK, OSDK, for automated control, enabling smooth transitions during testing. An onboard computer processes and executes the commands in real time. The mathematical model is the core of our methodology. It describes how the UAV moves in space, kinematic model, and how its velocities change based on its internal dynamics and the environment, dynamic model. We simplified the kinematic model by excluding roll and pitch angles, as these are stabilized automatically by a low-level controller, allowing us to focus on horizontal motion control. The dynamic model captures the UAV's velocity changes, considering factors such as inertia. To ensure accuracy, we calibrated the model with experimental data, making the simulations closely reflect real-world behavior. The goal of this work is to solve the trajectory following problem. We evaluate three controllers to compare their performance: a purely kinematic controller that calculates the necessary velocities, a dynamic compensation controller that incorporates the dynamic model for more precise adjustments, a model predictive controller, or MPC, which optimizes the UAV's decisions by predicting future behavior and accounting for constraints. First, with the kinematic controller, we observe the UAV following the defined trajectory in the real experiment. The comparison between real and simulated results shows consistency, although errors arise in more complex conditions. With the dynamic compensation controller, the UAV adjusts better to external disturbances. Graphs show trajectories closer to the desired path, both in simulation and real experiments. Finally, the MPC achieves optimal performance, anticipating deviations and significantly reducing errors. Graphical comparisons demonstrate greater precision in trajectory following, highlighting the controller's ability to adapt to real-time changes. In conclusion, this work demonstrates that digital twins, combined with advanced sensing technologies and a ROS-based communication channel, are effective tools for ensuring UAV accuracy and stability. The implemented methodology has facilitated a smooth and reliable transition between simulation and real experimentation, although challenges such as external disturbances remain. Finally, this approach provides a solid foundation for future developments in simulation reality integration, enhancing UAV reliability and safety in real-world applications.